Welcome to Space Nuts. I'm your host today, Heidi Campo, and I'm here with Professor Fred Watson, astronomer at large, and we are going to be answering some of your questions today.
15 seconds. Guidance is internal. 10, 9, ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
So we have a question from Keith Wilson. Keith did not list where he was from. Are you from Earth, Keith, or are you hailing us from another planet? That would be my question for Keith. Keith's question for Fred is, I have a question. Because the sun burns its fuel so fast, how much smaller is it now compared to its size 2 billion years ago?
And there's an answer to that, which we can calculate. We weren't around 2 billion years ago, so it's not easy to measure it then, but we can work out what it was by the rate at which the sun is burning its fuel now. So the sun goes through, and these numbers always stagger me, roughly 4 million tons of fuel, hydrogen fuel, per second. And that means you think, my God, that's an awful lot of hydrogen every second. That's what it's turning into helium. And it's that process, the nuclear fusion, that is releasing the energy that we see with all the light and the subatomic particles and everything that comes from the sun. It is the underlying process is that nuclear fusion. There is also... I've not seen this statistic before, but I did look it up. About 1.5 million tons per second, that is the solar wind. That's the particles coming off the sun. So there's this loss of about, roughly 5 million tons per second. So you can do the calculation. And it turns out that what saves the day is the sun is very big. It's got the huge amount of material in it. When you think of it, it's 100 times the diameter of the Earth. It's a very, very massive object. So there's a lot of it. So that release of energy and solar particles over its lifetime, 4.6 billion years, amounts to a loss of mass of, wait for it, 0.05%. It's virtually negligible. The sun's mass has changed, but by a very tiny amount. There's a number of places on the web where you can find that calculation, but that's what we believe. It's lost mass, but it's only lost a tiny amount compared with the mass of the sun itself.
That's interesting. I have never thought about that, but it's good that this is something that doesn't need to also keep me up at night, along with the other things I worry about. Our next question is from Michael, who is in New York.
Hello, this is Mike from New York, and I have a question about primordial black holes and dark energy. I believe you guys have addressed questions before about primordial black holes and how a concentration of them could result in dark matter and the gravitation that we observe behind them. And that's, I believe, generally been disproven. My question is, how could primordial black holes potentially relate to dark energy? If we assume that they are spread evenly across the universe, if there's a sufficient amount of them, as they evaporate, and that loss of gravitation goes with them as they evaporate, could that explain the increased acceleration of the expanding of the universe being driven by dark energy? I'm just curious to know if you've heard of that being tossed about before as an idea. And as I imagine, the math doesn't bear out. Has any studies been conducted to definitively say that is not the case? Thanks, guys, and keep up the good work.
Yeah, thank you, Mike. Good question. You're right, the math doesn't bear it out. But the bottom line here, well, two things, I guess. what was it that basically got rid of the idea that dark matter was made up of primordial black holes? It was experiments done in the 1990s, to look for the gravitational lensing effect. If we had a universe that was filled with black holes that we couldn't see because they weren't gobbling anything up, so they didn't glow in X-rays as you do when you're gobbling stuff up if you're a black hole, those black holes should have distorted the images of stars behind them, magnified them, and we should have seen these. If we measured the brightness of large fields of stars regularly, we should have seen stars brightening and dimming all over the place due to all these black holes, and that was not seen. It was an experiment called MACHO, and MACHO actually was basically the acronym for those objects, massive compact halo objects, MACHOs. So it was at that point that we decided it wasn't MACHOs, it was WIMPs, WIMPs being weakly interacting massive particles, and that's what we've been looking for ever since with dark matter, and not finding it, I have to say. But then going on to your comment about black holes relating to dark energy, black holes do evaporate. We know that from the effective, the theoretical work that was done by Stephen Hawking back in the 70s, actually, that demonstrated that there is a radiation that comes from black holes. It's by quantum processes rather than relativistic processes. And that is called Hawking radiation. And what it leads to is the evaporation of black holes. But the timescale for that doesn't tally with the dark energy problem. Black holes evaporate, but on timescales of tens to hundreds of billions of years. It's a slow process, and it's hard to imagine how that could contribute in any way to the dark energy that we see that is making the universe expand ever more rapidly. So a nice idea, which I think doesn't, exactly as you said, doesn't hold up because of the mathematics. Thanks a lot. Thanks again, Michael.
Yeah, that's very, very interesting. A lot of deep thinking questions here.
Yes.
Now let's take a break from the show to tell you about our sponsor, Incogni, and get ready to write down the URL and the keyword to get a special deal as a Space Nuts listener. Do you ever wonder just how much of your personal information is floating around the internet? Your name, your phone number, even your home address, all being bought, sold and shared by data brokers you've never heard of. And guess what? That's why your phone won't stop ringing with spam calls, your inbox is overflowing with junk mail, and you're more vulnerable to identity theft than you probably think. That's where Incogni comes in. Incogni is a powerful, automated personal data removal service that fights back for you. Once you sign up, Incogni scans over 200 data brokers and sends legal removal requests on your behalf. And all you have to do is sit back and they'll do all the heavy lifting, filing requests, doing the follow-up, keeping you updated every step of the way. And within weeks, you'll notice fewer robocalls, fewer spam emails, and less of your personal information floating around for cyber criminals and marketers to grab. It even helps reduce the risk of being caught up in identity theft or phishing scams. And the best part, with Incogni's annual subscription, they don't just stop at one sweep. They keep scanning and sending removal requests on repeat, so you stay protected all year long. Right now, through this link, you get an exclusive 60% off with the code SpaceNuts, plus it's risk-free with their 30-day money-back guarantee. Incogni.com/spacenuts. That's the URL. INCOGNI, incogni.com/spacenuts. Protect your privacy, stop the spam, visit incogni.com/spacenuts and the special word space nuts to get that great deal today and take back control of your data. Now, back to the show.
3, 2, 1.
Space Nuts
And speaking of deep questions, we have Duncan Sargent from Weymouth.
Yep.
It's a follow-up question, and it is a thesis that he's having me read here. So buckle up, listeners. We have the question of the episode coming at you. Hello to both of you. This is a follow-up question from one I asked ages ago, well over a year if I recall. It was the one about how can two black holes merge into one if no mass can come out of a black hole. Neither can take the matter from one to the other to become one. Of all the questions I have sent the answer to, this is the one that was the least satisfying I felt. Normally, I feel you give good answers, but on this one, this is the one that I was suggested that I read up on the process. Well, I have spent months doing this. He has done his homework. He has read it. And I still do not have a definitive answer, but I will lay out what I have discovered. Basically, as black holes near merger, something happens within them that creates massive amounts of gravitational waves. This accounts for roughly 10% mass loss in the eventual combined black hole. I initially thought this mass loss was from the event horizon only, but apparently not. And the actual black holes themselves lose mass. Now, neither mass or energy can escape the black holes, but apparently this is what the math says, and words can't really describe it other than just to say that the math says so as it does. It is something to do with the mass energy that is not really defined in the way that we think it is, and it becomes a bit fuzzy. The gravitational waves are in space-time itself, and the whole merger process is somehow carried out with the actual confines of the space-time they occupy, rather than the actual black holes themselves. As we know, neither of them can actually take mass from the other. Apparently, at the very last point before they merge, each black hole sends out a very thin tentacle of something, which when they touch together, the merger happens. However, whilst this mathematically defined, it is not able to be easily defined by words. So, could Professor Fred please attempt to put into words for me, as with all the reading I have done, my head hurts and I cannot think of a way to put it myself. How much does matter from one black hole, or two of them, get extracted from the other and combined? What happens to the actual singularity? Do we end up with nested singularities? And how can that exist? Please help me understand in easily defined English. I get impressed from what I have read that a lot of this comes down to the math that says that we see it happening, so it does. But we actually don't know how. Is that pretty much it? Okay, thank you for looking into my follow-up. I look forward to your podcast each week, listening carefully for new snippets of information. Please keep up the good work.
Well done, Heidi.
Thank you. Duncan put me through the challenge, my first Q&A.
Yeah, it's like a script for a whole show. But thank you, Duncan. Duncan, a fellow Brit living in Weymouth there in the south of England. Always nice to hear from him. But this, look, Duncan, this is it's a challenging thing, and it challenges the whole of astrophysics. Because we don't really know what happens to black holes within that last 3.26 light years is the number. It's called the final parsec problem. A parsec is a distance. It's what astronomers measure rather than light years. You can't measure light years because we don't have stopwatches good enough. But a parsec is 3.26 light years, and it's what we, in the trade of astronomy, what we actually talk about. So the final parsec problem is that there's not the way the energy from the merging black holes is released into gravitational waves, which is exactly what you've said. That is the issue. How does it happen? I'm going to read a paragraph from Actually, space.com, one of the websites that we are big fans of at Space Nuts, they had an article a few years ago called "What Happens When Black Holes Merge?" And I'll read a paragraph from that because it sort of illuminates what you said and actually sort of quotes. Almost quotes to the letter what you had in your question. The final parsec problem, reading now, is currently an unsolved riddle in astrophysics. But whatever mechanism takes place, eventually black holes get close enough that the gravitational waves can really pull a lot of energy from the system. At this point, the black holes only have a few seconds before they merge. At those close distances, the black holes start to deform each other. They don't really have surfaces. The event horizons are just invisible boundaries that mark the region of no escape. But the shape of the event horizon depends not just on the black hole itself, but also the geometry of space-time around it. So as the black holes begin their deadly dance, the event horizons elongate and stretch towards each other. We understand what happens next only through complex computer simulations that monitor and track the evolution of the event horizons. In the milliseconds before impact, each black hole sends out a thin tendril, a tiny tunnel of its event horizon towards its companion. These tendrils meet and merge, forming a bridge between the two black holes as if they were connected by an umbilical cord. Very quickly, the bridge widens and the event horizons glue together like two colliding soap bubbles. Within an instant, the black holes merge into one. But here's the crunch. What happens inside is anybody's guess. The center of a black hole is known as a singularity, a point of infinite density. This is where our current understanding of physics breaks down. Simulations show that the singularities quickly find each other, briefly orbit, and then merge. But what actually happens is unclear. So, Duncan, your question is at the forefront of astrophysics, and I applaud you for asking it. I don't think you'll find this answer satisfactory, as you've commented before, because you're asking questions that really we don't have answers to. But thank you for getting your head around the problem in the way that you have, and thanks again for your question.
Fred, are there any theories?
Yes, theories abound.
What are the leading theories?
Well, it's basically what we've said. That somehow the black holes actually come together. There's a sort of all this happens very much in the last few milliseconds of a merger, and that's the bit that we see with the gravitational wave records that we get from instruments like LIGO, the Large Interferometric Gravitational Wave Observatory, and other gravitational wave detectors. So somehow they come together. There is a phenomenon which is talked about in black hole merger parlance as being the ring down. And this is when the merger is complete. The gravitational waves from the collision have been emitted. They've basically stopped. They switched off. And the thing rings down. And it's got, I suppose, implications of something vibrating. So it may well be that there is a bit more to the story than what we've just been talking about. But that's after the event. That's after the collision has happened. And Duncan's problem is trying to understand how something that that won't let go of any mass, how it can come together with something else. And the answer is it does.
I think of this, this might be the strangest metaphor you've ever thought of for black holes, but I'm thinking of this like cooking an egg. If we have two cracked eggs in a frying pan, the yolk would represent the singularity and the white would represent the event horizon. If these two eggs were to, let's just say, because eggs don't do this, but let's just say they were being pulled towards each other and merged, that point where they're merging is when the yolks both break. So there is kind of a point where it's two broken eggs, but then if they merged together to form one super egg, there would be something going on there. I don't know. This is how my brain is trying to wrap around these really complex problems, is something as simple as food.
Food's a good way to do it. If in doubt, turn to food. And so I think it's a good metaphor.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
All right. So our last question for today is from Lawrence Ingham, and this is a audio question.
Hi, Fred and Andrew. It's Lawrence from England here. I have a question about your favourite subject matter, that being dark matter. And I'll cut straight to the chase. Could dark matter not simply be energy manifest? And what I mean by that is, it seems that during really intense periods in the universe, we don't really have the current scientific models to explain how those processes occur. And my main example will be the epoch of inflation, where such a rapid expansion of the universe in such a small period of time, to me, seems as though there must be processes going on there which we just do not understand. And we cannot recreate, we cannot test it, but there must have been, in such an intense period, certain processes in which events happened which created things like, potentially, dark matter. And when you look at the expansion of the universe and reasons why there's all this unaccounted mass, all these things we attribute to dark matter, could that not potentially be simply energy manifest? During that epoch of inflation, energy itself could potentially have been transformed into a different type of matter which we do not understand yet and cannot understand, but that would explain why the universe is expanding. It would explain why we can't visualize and test dark matter, because once that energy has been used, you can't then test it because it's expanding the universe. And I guess it also somewhat aligns with Einstein's equations with energy and mass being almost interchangeable. I don't know. It seems that as there are certain periods in which we cannot explain what was going on and our current scientific models aren't fit for purpose because those events are so unique and so extreme. Is this something that's been explored? Is it something that's currently being explored? I'd love to hear your answers. Many thanks.
So yes, in fact, the answer is, Lawrence, you've basically said exactly what the situation is as we understand it. Sorry, I'm pausing for words there, trying to find new words. So the idea of dark matter being energy manifest, in other words, energy turned into matter because they're related by E equals mc squared, is how we think it got there. That's how what we think the origin of dark matter is. Within the Big Bang itself, which was an energetic phenomenon that very quickly created the matter that we see in the universe. So it's some of the processes are actually quite well understood. It's not that we're not understanding that. It's just when it happened, that it happened right at the beginning. The dark matter was created at the same time, whatever it is, was created at the same time as the normal matter, what we call the baryonic matter, and basically formed this, as the universe expanded, formed this web of material that we call the cosmic web, and that led to the distribution of galaxies that we see today. So the answer to your question is yes, but it doesn't change the issue. Yes, energy was turned into particles, but we don't know what those particles are. The dark matter particles are as yet undiscovered. It's some form of subatomic particle, which is very important in the universe. We think it's why galaxies formed. Without it, maybe they wouldn't have formed. So the quest is still on to find out what dark matter is, but you're right, it came from energy.
Excellent, Fred. Well, I feel enlightened myself. These are fantastic questions. And it's interesting, there's always so many questions that everyone always wants to ask about dark holes and dark matter. And the big heavy hitting questions is the questions that all humanity has. And I think that that's just the exciting thing, is to remember that's the thing in space, is there's more questions than there are answers. And we do our best on this show to provide answers, but ultimately, it's up to the scientists and the people who are discovering these things. And you can even get involved as a citizen scientist. I'll give a little plug for NASA and some of the opportunities they have for free online. You can help contribute to some of this research. If you look up citizen science with NASA, that's something you can get involved with yourself.
Always a fan of citizen science. Absolutely. Some great things have come from citizen science, Heidi.
Yeah, absolutely. Do you have anything else you'd like to say about citizen science?
No, we might have a chat about that down the track in one of our upcoming episodes, because it's such now a fundamental part of what we do. It's very, very important, not just in astronomy and astrophysics, but of course in the whole world of research, whether it's botany or ecology. All of those things can benefit from citizen science.
Yeah, well, and there's the really fun one. If you guys have telescopes and you're into astronomy, as I assume these listeners are, you can even look up some of the exoplanet opportunities that you can have with NASA to try and help discover and identify exoplanets. But with that being said, I think we've answered some questions, we've gave some questions, and we have more questions yet to answer. So, Fred, thank you so much. That concludes another Q&A session of Space Nuts.
Great pleasure, Heidi. Always good to talk, and we'll speak again soon.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.